It's my pleasure tonight to introduce what is the first of our offerings for this year, and it's a subject on light, and it's going to be given by Dr. Bukowska and Andrea Curatolo. They are going to have a sort of interactive presentation, at least between themselves. You will have your opportunity to interact at the end of the talk. So.
Thank you so much for a very nice introduction, and good evening everyone. It's our great pleasure to be here to talk to you about the science of light. Light that sometimes is obvious, sometimes mysterious. The light that can be visible or invisible. Andrea and me have been very fortunate to work in optics field for the last few years. We both have been involved in development of different instruments that use light as a source of information that have been applied to medicine, art and biology. And we hope that you will enjoy this short introduction to optics that we are about to present. So if we close our eye and imagine if there were no light from the sun, no plants would be able to grow because plants rely on light to make food. Animals and then humans would have nothing to eat. Sunlight is the source of most of energy on Earth. Without the sun, the world would quickly become very cold and the water would freeze. Very soon there would be no life left on Earth. Without light, we couldn't admire the beauty of morning sunrise, magic sunset in the evening. Without light, we couldn't see rays trapped by a spider web, or funny light refraction in the swimming pool. Without light, we couldn't actually see what is inside, and we probably wouldn't ask questions. We couldn't see beautiful northern lights, and we probably wouldn't be very happy. But actually, what is the light?
Thank you, Danka. Well, light is a traveling electromagnetic wave, and as such, it's got its own wavelength, which is the distance between two peaks, and its frequency, which is the number of times per second that one point in space is hit by two consecutive peaks. Now, the frequency and wavelength of electromagnetic waves cover a broad spectrum from kilohertz, or hundreds of meters, for radio waves, to billions of terahertz, or subatomic distance, for X-rays and gamma rays. In a small fraction of this spectrum, around hundreds of terahertz, or hundreds of nanometers, there is the visible light portion, which is the one we can see with our naked eyes, which is bordered by the infrared on the long wavelength side and by ultraviolet on the short wavelength side. But just how is this electromagnetic radiation generated? Let's use the example of an electric wire subject to alternate current. Now, the electric field generated by the moving electrons produces a magnetic field around the wire. The magnetic field strength changes with the velocity of the electron in the wire. Now, the change in magnetic field induces an oscillating electric field orthogonal to the magnetic field line. And this in turn generates a magnetic field, which in turn generates an electric field, and so on and so forth. And the succession of induced fields result in electromagnetic radiation. But how does it propagate in space and time? Well, from Maxwell's equations describing the relation between electric and magnetic field, a wave equation can be, for both fields can be written. And its solution is a traveling sinusoid, both in time and space, at the speed of light, with the electric and magnetic field orthogonal to each other, and concatenated in space. Now, this graphic here shows it only in one dimension, but if we extend this concept to 3 dimensions, we have a spherical wave, where green represents the peak of the electric field and red the troughs of the electric field, and the magnetic field lines are drawn in white. Another solution to the wave equation is the plane wave, which can be seen as a superposition of in-phase spherical waves, all aligned on the plane, as suggested by the Huygens principle. Now, two fundamental laws of light interaction with either metals or dielectric materials like glass are the laws of reflection and refraction, as formalized by Snell and Fresnel. Now, given the wavelength, refractive index, and geometry of the material illuminated by light, they describe the direction and power of the resulting wave, as shown here. Now, this law gives us great power for interacting with light and manipulating it to deliver power or information where we want it. Let's take the example of a curved surface now, basically a section of a sphere, a so-called planoconvex lens seen here in cross-section. When hit by a plane wave, the refraction will turn the plane wavefronts into spherical wavefront, with its center closer or further away from the lens, depending on the material and radius of curvature. Now, the distance from the lens to that point is called the focal length of the lens. A smaller radius of curvature results in a shorter focal length. In this simulation video, we see the converging spherical wavefront formed by focusing of this shorter planoconvex lens. Now, there's a catch. Another fundamental law of the interaction of light with finer aperture objects, as in the case of any real-life lens, called diffraction, limit the smallest spot size a wave can be focused down to about 200 nanometers diameter for visible light. Now, this is an important implication because, for example, in microscopy, this means we won't be able to see any details on a sample smaller than this size, or in laser manufacturing, we won't be able to engrave any details smaller than this size. A fourth fundamental property of light waves, and all waves in general for that matter, is interference, which is key in a variety of applications. Just like in a pond where waves generated by two stones thrown at the same time create patterns that somewhere add constructively to higher peaks and lower troughs, and somewhere else add distractively to leave the water surface unchanged, the same happens with light here. Now, let's imagine that this plane wave is going to hit a screen that has two pinholes separated by a certain distance. Another rendition of this experiment will be with two slits, as we shall see later. Now, two hemispherical waves are generated past the pinholes. In some location, the intensity will be stronger, in others will be weaker, or even consistently dark, as seen in this areas there. Now, when we detect the resulting wave, considering that the speed at which the light wave travels and the response of any detector, which could be our eyes or a camera, we're only sensitive to a time average intensity, which is shown here in bright green. Now, by adjusting the distance between the slits, or the pinholes, we can determine where the patterns of brightness and darkness fall, giving us a great control over light power and location. So we spoke of light detection. So far, all the phenomena we've encountered, which set the basis for harnessing the power of light for multiple applications, only require wave theory to explain light behavior. Now, light detection, say by a camera, especially at low light intensities, can only be explained by quantum mechanics, which requires to overcome the duality and apparent contradictions of a wave theory of light and a particle theory of light, where individual light energy packets called photons make up the stream of light. So in this animation, we go back to our double slit experiment, and we first see how particle theory will not explain the interference pattern visible on the camera or a screen. These light particles, these light particles would be absorbed at random positions behind the two slits, not giving rise to the interference pattern. As we saw before, the wave theory explains well the interference pattern, but only for a high source power with the dark and bright bands spacing dependent on the slit separation. But if we dial down the power of the light source, one would expect to observe the same interference pattern, just dimmer. It turns out that at low energies, low source energies, the camera records single pixel activation. So the light is only detected in one point in space at a time, giving way for a particle absorption explanation. Now the catch is that if recorded for long enough time, the intensity pattern that will be generated one pixel at a time is that of a wave interference. So light inherently behaves both as a wave and a particle, depending on the type of interaction we're subjected to, propagation or detection, for example. But it carries elements of both in it. As we just saw, absorption is an important light-matter interaction. Another one is scattering, which takes place when light interacts with material, the size of which is similar to the wavelength, so for visible light microns, say crystal impurities, dusts, or human or animal cells. In simple terms, absorption can be seen as energy transferred from light to matter, and scattering as energy spatial redistribution. Now, these phenomena are unwanted in some applications, for example, in fiber optic communication, but are very important in other applications, like energy generation or imaging. Absorption in crystal or glass needs distances on the order of hundreds of kilometers to attenuate light to extinction, but in biological tissue, that distance becomes only a fraction of millimeters, and it's highly dependent on wavelength, as shown in this graph. With the goal of higher penetration depths for light in biological tissue, as required for imaging below tissue surface, light wavelengths in the so-called near-infrared region window are chosen, as they're not well absorbed by water, which makes up most of the biological tissues. A very important physical process that can happen after light is absorbed is fluorescence. It consists of re-emission of light at longer wavelengths, so lower energies, after some initial energy dissipation takes place in the absorbing molecule called fluorophores. Fluorophores are very specific emission spectra, so they emit light at different colors with characteristic intensities, and they're excited by absorbing specific colors of light. This makes up for a strong molecular specificity, which allows to use fluorophores and bind them chemically to molecules inside molecules of interest inside cells and biological tissues to observe and image physiological and biological processes that otherwise be unobservable. So it is a vital tool for molecular biology and many other branches of science. So let's see how it works. So after light absorption, the fluorophore molecule is excited from its ground energy level to a higher energy level, and this process is called excitation. Now, there are several energy levels that the molecule could be excited to. The molecule is unstable at higher energy levels, so it naturally releases its energy in a non-radiating fashion. Yet it's still excited, and the time it takes before re-emitting light at lower energy by returning to the ground energy level, it's called fluorescence excited lifetime, and it could be in the orders of nanoseconds. After that time, energy is released as a new light wave, incoherent with the absorbed excitation wave. That means that the phase of that light wave and its directionality are not identical to the excitation wave, nor to the other waves generated by other fluorophores being excited by the incoming light wave. So a similar process takes place in the laser, short for light amplification by stimulated emission of radiation. Molecules in a confined chamber called the active medium are excited to higher energy level by absorption of energy, sometimes provided by another light source. So as in the case of fluorescing molecules, the active medium molecules, which could be of solid or gas medium, after excitation release energy in a non-radiating fashion rapidly to sit at lower but more stable excited energy levels, just shown in those graph there. Now, stimulated emission, as discovered by Einstein, is a process for which a molecule in an excited state could be forced to emit before its spontaneous decay to the ground level if struck by light with photon energy corresponding exactly to the excited energy level. So the trick is to add a feedback mechanism for which light is fed back and forth through the active medium cavity at a distance which keeps a standing wave inside. And this is done by adding two partial reflecting mirrors that let some light escape from one side but keep the amplifying seed wave inside the medium. When the appropriate active medium is selected, excited by absorption at the proper wavelength and power, the mirror reflectivity, shape and distance is suitably chosen, laser light will come out at one end. Danka will tell you a whole lot more about the amazing properties of laser light. Another desirable way of manipulating light is to deliver it within a cable. That could mean that we could transfer information within it from distant location, or we could bring light inside orifices and all the organs of animals and human patients, or in dangerous areas. Now the optical fiber or rectangular waveguide, as depicted in this video, is nothing more than a minute irrigation canal in which we'd like the light wave to propagate into. In our case, this canal is a flexible string of glass, often made of 10 micron or less diameter silica core, surrounded by 125 microns, so about the thickness of a hair, glass cladding with lower refractive index. To do so, we first have to couple the light into the fiber core by tightly focusing, as we saw before, the light wave to one end of the fiber. Once we've done that, as you can see in this video, only certain light wave distribution, called modes, will propagate from end to end, as in the case here shown for transverse electric 1-0 mode. Depending on the waveguide or fiber core size and the light wavelength and the focus spot size at one end, one or more of these modes can propagate into the fiber. And here it's another mode that is shown, called TN01. Now, more than one mode can propagate at the same time, and depending on size, several other modes that are not shown here could propagate. Now, if we modulate the light carried by these modes, we allow to transfer information from one side to the other of the fiber, which opens the gate to the whole telecom industry using light. But now I will leave.
All of those discoveries discussed by Andrea, like interference, reflection, refraction, laser, wouldn't be made without the curiosity and imagination of open-minded scientists. One of them was Ibn al-Haytham, also known by the Latinization Al-Hazen, an Arab scientist, mathematician, astronomer, and philosopher. He made significant contribution to the principle of optics, astronomy, mathematics, meteorology, but also to visual science and the scientific method. In the field of optics, he made the observation, for example, that light rays travel in straight lines. He also studied the process of sight, the structure of the eye, image formation in the eye, as well as visual system. Although English physicist Sir Isaac Newton is most famous for his law of gravitation, he was also instrumental in the optics revolution of the 17th century. He's perhaps the famous scientist in the history. With discoveries in optics and motion, Newton developed the principles of modern physics. Newton built the first practical reflecting telescope and developed a theory of color based on the observation that a prism, which is visible here, decomposes white light into many colors of the visible spectrum. In early 1670s, Isaac Newton presented his theory that light was composed of particles. Only 20 years later, Dutch mathematician and scientist Christian Huygens proposed a wave theory of light. Huygens, like Newton, was also a leading scientist in the 17th century. Except introducing a theory that light is a wave, his work included early telescopic studies of the rings of Saturn and the discovery of its moon Titan. Wave nature of light were also confirmed by experiments conducted by Augustin Fresnel and Thomas Young. Fresnel was actually a French engineer and scientist, but he's perhaps best known not for wave nature of light, but as the inventor of the Fresnel lens first adopted in lighthouses while he was a French commissioner of lighthouses. Wave optics was also successfully unified with electromagnetic theory by a Scottish scientist, James Clerk Maxwell. Maxwell demonstrated that electric and magnetic fields travel through space and waves moving at the speed of light. Many physicists regard Maxwell as the 19th century scientist, having the greatest influence on 20th century physics. Famous US scientist Richard Feynman wrote about Maxwell that from a long view of the history of mankind, seen from, say, 10,000 years from now, there can be little doubt that the most significant event of the 19th century will be judged as Maxwell's discovery of the laws of electrodynamics. I think that Albert Einstein is a person that doesn't need really introduction. This great scientist was born in Germany and developed the general theory of relativity, one of the two pillars of modern physics. Einstein is best known in popular culture for his mass energy equivalence formula. However, what is maybe not well known, he loved music. He played the violin, admired Mozart, and if he didn't become a physicist, he probably would play in the orchestra. Important discovery to modern physics and our life eventually was made not so long ago in US by Charles Hart Townes. He created a microwave amplification by stimulated emission of radiation, which is a device that produces coherent electromagnetic waves at microwave frequencies. Based on theoretical work done by Townes and leading to Masser, first laser was then created by Theodor Lyman in 1960. Charles Kao and George Coham of the British company Standard Telephone and Cables were the first to promote the idea that the attenuation in optical fibers could be reduced below 20 decibels per kilometer, making fibers a practical communication medium. They both proposed that the attenuation in fibers available at the time was caused by impurities that could be removed rather than by fundamental physical effects such as scattering, what Andrea discussed before. They correctly and systematically theorized the light loss properties for optical fiber and pointed out that the right material to use for such fibers, silica glass with high purity. And this discovery earned Kao the Nobel Prize in Physics in 2009. So scientists not only have conducted experiments to explain light behavior, but they have been strongly involved even in light creation. Actually, humans have been able to create and control light for thousands of years. The earliest form of lighting was with fire, such as burning wood, candles, gas. Now, the most convenient source of artificial light is the electric light, such as neon lights, fluorescent tubes, LEDs, and laser. Why lasers are so special? First of all, laser different from other sources because can emit light coherently. This spatial coherence allows a laser to be focused to a very tight spot. Spatial coherence also allows a laser beam to stay narrow over great distances. And lasers can also have high temporal coherence, which allows them to emit light with a very, very narrow spectrum. These all make lasers very special to application, and Andrea will briefly talk about laser application in telecommunication and manufacturing.
Thank you, Danka. application of light-based technologies found, and by no means this is an exhaustive list, but we're trying to cover the breadth of applications that light and light-based technologies have. So telecommunications, manufacturing, renewable energies, lighting, arts, biomedicine, these are all fields where lights and light-based technologies and laser make a very important, have a very important position. So let's start with telecommunications. Now, the internet is powered mostly by optical fiber networks that only in the wide local area transform light signal into electronic bits of information. Now, the internet traffic per person in 2015 was equivalent to 44,000 3-minute phone calls per month. Even I, being Italian, I don't call home that often, so that's because there's so much information under a variety of media traveling from side to side of the globe, and it's only going to increase in the future, as you see in this graph. So its sustainability is currently guaranteed by two factors. Semiconductor laser at a wavelength of 1550 nanometers, which are cheap, robust, compact, and long, and have a long lifetime, and submarine optical fiber cables, which will reach a length of 2 million kilometers in 2018. Here in this video, it's just showing the amount of cables that are laid on the ocean floor. Yeah, it's pretty outstanding. In manufacturing, high-power lasers can be used for marking multiple types of material, from ceramic to plastic to metals, from a simple black mark to a variety of color marks, for precision cutting of the fine materials, or for high-output industrial process applications for a variety of material and thicknesses, for welding, regardless of the material thickness or the similar metals, from fuel cells and batteries through fine wires for medical device could be welded, for drilling, for engraving all metals and industrial ceramics, for ablating, so for precision layer removal from metals and industrial compounds such as elements used within electronic products, for additive manufacturing in many rapid metal powder manufacturing processes, and also for cleaning, typically using high repetition rates and short pulses with high peak powers, with the intention to remove surface debris and contaminated layers without damaging the substrate material. And all of this in a variety of industries, from aerospace to automotive, to electronics, medical, and solid-state laser. I mean, that the active medium that we talked of before, it's either gas or, for example, fiber. So especially neodymium YAG and fiber lasers, either in continuous wave or pulsed operation. Now the graph here shows the absorption spectra of many metals versus wavelength, and also the line of the narrow lines of emission for the lasers of interest. Here, this video shows just some of the capabilities of a fiber laser in industrial cutting, welding, and also some drilling operation. So, for the renewable energies, I let Danka say a few words.
So everyone probably knows that photovoltaics is an important method to save natural environment and money. This technique converts solar energy into direct current electricity using semiconducting materials that exhibit the photovoltaic effect. The direct conversion of sunlight electricity occurs without any moving parts or environmental emission during the operation. Solar photovoltaics is now, after hydro and wind power, the third most important renewable energy source in terms of globally installed capacities. more than 100 countries at the moment use photovoltaics. Although today photovoltaics deliver only 1%, so we are somewhere here, of the world electricity, it is predicted to be 27% by 2050. Another great example of light sources that help to save natural environment and, again, money are light-emitted diodes, or LEDs. LEDs actually revolutionize our technology, giving a promise for minimal environmental impact, generate immense economic value, and the power to change our lives for the better. Energy saving from 50 to 70 compared with conventional technologies result in similar cuts to carbon emissions. However, still we need to find a way to make those lights cheaper. With LED technology, it's easier to control directionality of light. LED lights optimize our safety and security. For example, there was a dramatic increase noticed in Toledo public schools in the US in the quality of light of local communities, since LED lighting makes pictures more visible on security cameras. Supermarket shopping is a highly visual experience, and it's important for our retailer to show items in their true and most appetizing colors. LED lighting is a must-do solution. It offers tremendous energy savings, great quality of light, and it's also fantastic in terms of maintenance and goodness. Cool light, as we see here, is probably the best choice if we need to study, work, or just read a book. However, lighting can be also used to create emotions in our houses. It includes the use of both artificial light sources like lamps and light fixtures. However, natural illumination can be also used by capturing daylights. Natural light can also create world, like presented here, bringing the ancient Middle East to the Midwest in movies. Lighting or illumination attracts, impresses, and welcomes visitors of public spaces. And whether we are in Vietnam, New Zealand, USA, Sweden, England, or we are standing in front of Council House in Perth. Lighting can bring art, technology, music, and joy to one place. Vivid is an annual outdoor lighting festival with immersive light installation and projection in Sydney. Part of the lighting festival also includes the performances from local and international musicians and an ideas exchange forum featuring public talks and debates from leading creative thinkers. The centerpiece of Vivid Sydney is the light sculptures, multimedia interactive work, and building projections, as visible here, that transform various buildings and landmarks. Only in 2013, the festival attracted more than 800,000 people to the outdoor exhibition and events, and generating around 20 million in income for the state. In 2013, the University of Western Australia celebrated its centenary and ranking as a world top 100 university. A year of special events were held to acknowledge this 100th birthday. On this occasion, the UWA campus was transformed into a kaleidoscope of color and sound, what we could see in this animation. And to continue the topic of arts, I will let Andrea to talk about this topic.
Thank you. We're taking a slightly different spin here because I'm going to talk of light-based diagnostic in works of art, which is used to investigate constituent materials of, say, paintings, for example, so pigments, dyes, organic compounds. Also to analyze execution techniques for dating and authentication purposes to verify former restorations and also for the choice of new restoration materials and also for precautionary conservation. So in the photo here you can see me and a professor from Politecnico di Milano, my alma mater, deploying a portable diagnostic system at the Collegiata of the Basilica in Castiglione Olona in Italy. In this fresco series by Masolino da Panicari in the Collegiata, there was a strong need of a verification of former restoration that might have not been reported, and precautionary color conservation. So we've done this using an hyperspectral reflectance system and a fluorescence system, and the combination of the information provided allowed to recognize different fluorescence signature of both authentic and restored pigments. Diagnostic is also used in biomedicine using light techniques. In biology, for example, light is used as a diagnostic tool using fluorescence microscopes, like 2 photons, confocal, super resolution microscope, which allow the study of molecular, cellular, and physiological processes in vitro, and sometimes even in vivo with subcellular resolution. They allow formidable progress in the study of neurology, for example, neurology and disease, by the use of animal models, as seen here in this exquisite image of half a millimeter of a mouse brain, or showing this complex 3D neural networks with exquisite 3D resolution capable of detecting single neuron synapses and metabolic activities. But all of this is confined to the realm of biology and animal models, as it uses contrived setup, like animal window chamber to overcome the short light penetration in biological tissue. So in medicine, instead, light-based technologies are used to enable detection and identification of diseased tissue in pathology labs, like cancer cells in breast biopsies or excised tissue lumps. Bright field, dark field, phase contrast microscopy are standard of care in histopathology labs. Now, the potential problem with that is that it's rarely done on the spot. It usually takes days. It requires tissue excision, fixation, dehydration, embedding in wax, so a lot of processing and slicing and staining. It is the gold standard, but because of all this processing, it's a long way away from the live tissue, so there could be artifacts that efficient the diagnostics. And the pathologists are required to undergo 10 plus years of training to read them properly. And so this is what this sample, histopathological sample would look like, and this is magnified. So we can recognize structures. We can certainly see the macro view. We can see the micro architecture. We can see details on the cellular scale, which bring out the diagnostic value of the technique, but subsurface information clearly is not available as for all the processing that the tissue is undergone. Another light-based technology used in medicine is video endoscopy. It's used to look inside all organs, and it does so by using fiber optic bundle and a camera. It is standard of care in screening and interventional pulmonology and gastroenterology. And with such technique, we can see the macro view, still some micro architecture, but there isn't just enough resolution to see cellular feature. So it's used more as a guidance tool, more than a diagnostic tool. And also there is no subsurface information behind the organ lumen. So endomicroscopy combines endoscopy and microscopy. And so it can provide cellular details still in an in vivo scenario. So it carries diagnostic information. So it shows a great potential. It's new technology development showing great potential and avoiding potentially the need of biopsies by bringing microscopy to the site of interest. It also provides some subsurface information, but with limited penetration depth to about 100 microns below the organ lumen. So a technique that both Danka and I have been working on that it's probably towards this holy grail of optical biopsies, basically giving diagnostic information without removing tissue. It's called optical coherence tomography. And it's an optical analogous of ultrasound imaging in that it uses time of flight of echoes of infrared light waves backscattered from a tissue sample at various depths to reconstruct a 3D tissue structure at high resolution, normally a few microns. It uses light interference to create first a depth scan of the tissue structure in one depth location. By then combining transverse laser beam scanning, like raster scanning, in 2 and 3D over the tissue, one can create 3D images, subsurface images, to 1 or 2 millimeters stiffness imaging, which could complement that provided by optical imaging. And now on to the International Year of Light, 2015. We'll know why.
So, isn't it amazing that light and light-based technology can support medicine, manufacturing, telecommunication, and even art? And this importance of light science has been recognized by the United Nations that established the year 2015 as an International Year of Light. By creating special observances, the United Nations promoted international awareness and action on these issues. The International Year of Light inspired more than 100 institutions from over 85 countries to promote the light and light-based technologies that directly improve quality of light worldwide. Light-based technology is a major economic driver with potential to revolutionize the 21st century. We could actually ask the question, why 2015? So, in 2015 we celebrated many major anniversaries, like 1000th anniversary of Ibn al-Haythar book of optics, 200th anniversary of Fresnel with Nature of Light, or 100th anniversary of Einstein general relativity. Also here in Western Australia, we were trying to be actively involved in organization of different events.
So, besides our role as researchers in our respective labs, I am the president of the Optical Society student chapter of the University of Western Australia, the University of Western Australia branch. Danka is the outreach officer. So we decided to start together with a few students and enthusiastic people with the idea, a chapter at the University of Western Australia, with the idea of bringing students and professionals dealing with optics and light, both locally and nationally, all to Perth. And we've done so during the International Year of Light with a lecture series called Light Talks, where Professor Eglinton from Uni Sydney gave an inspiring talk of light and technology. Professor Mackey, director of Mind's Eye Institute, gave a great talk on light in medicine. And also artist Rebecca Bauman showed light installation and exhibits around the world. We've also organized an outreach activity where we invited science communicators from Canberra, Professor Backer and Mr. Liam, to give a practical lecture with fun demonstration showing that actually lasers can do anything. And here you can see a video of the that it's available both on YouTube and our student chapter's webpage of the outdoor event that we organized on the beautiful UWA campus last November. And if it wasn't for this event, we wouldn't probably be here speaking to you, because just before the start, probably in this very moment, Greg came up to me and asked me if we were interested in giving a talk to you guys, and so we were, and so we're here. So you can go and bring up the counts on our website by checking this video on our website. Let me go ahead and say that there's been also a good hype around our activities. We made it to the Western Southern Weekly and some Science WA website, and also to the Australian Optical Society magazine. And so, in conclusion, we've presented the pervasiveness and beauty of light, tried to at least. We've given an extensive, but not necessarily exhaustive list of the physical properties of light, ways to harness it for the benefit of society, talked about the scientists and engineers that contribute to this development, the applications, the variety of applications of light-based technologies, Danka and my research focusing diagnostic bioimaging, the UNESCO International Year of Light 2015, and also our student chapters outreach initiatives. And with this, let us acknowledge the other OSA student chapter members and friends, the optical and biomedical engineering laboratories, all the collaborators at various hospitals and medical research institutes around Perth, the Lions Eye Institute, and the two professional societies that also provide financial support for our chapter. With this, thank you very much.
Well, if it was not exhaustive, certainly been comprehensive. Thank you very much, and we open the meeting for questions. Thank you.
I got lost about maybe 40 minutes ago.
Okay.
At the moment when you said, I've got momentarily up maybe. At the moment when you said absorption is when light turns into matter, or something similar to that.
Transfer of energy to matter.
Okay. So you're talking about when light hits something, it excites the molecules, and therefore it is transferring energy from the wave of light to the molecule by heating it up, exciting it, or whatever.
That's correct.
Until that energy dissipates by simply settling down again. Or where does that energy go then?
Well, there are several ways. So what I haven't mentioned is that there's scientists like to think that they can explain things, and so they need a few bearings, one of which is conservation of energy. So light energy is conserved, therefore light will be absorbed. The energy carried by light will be absorbed by the molecule. The molecule will increase its energy state. Now, it will decrease it either by vibrational or other things that lead to heat, for example, or by releasing it in the form of a light wave again. So, in that initial process, when I say it relaxes in a non-radiating fashion, it means that it's either by becoming hotter, it doesn't become really safe for a single molecule, but the medium becoming hotter, or other ways that don't involve emitting light, and then for fluorescence, for example, it emits it at a lower energy, which corresponds to.
So is reflection part of that return of energy?
You can combine all of the properties that, so refraction, scattering, absorption, all of that could be in there. But yeah, so.
Thank you.
Yes.
I'm interested, thank you for your presentation. I'm interested in the current limitations of laser, and I stress current, like today. For example, you show us a short video when laser was used in manufacturing and basically almost instantaneously cutting some kind of patterns. But the material was about 5 mils. Let's say, okay. What would happen how would that behave if the material was 50 mil or 500 mil right now? So,
Yeah.
so what's the limitation?
Yeah, so it depends. In some cases, you can't just dial up the power, given that you have enough power. So in some cases, you just don't. So you just have to accept that you're going to have to take longer to cut a little by little. Just by ablating, conceptually just by ablating a little more, and then that may also end up in some tapering of the cut. In other cases, you just think, okay, maybe I'll just dial the power up, but that may result sometimes, depending on the material you're doing onto incavitation and basically just creating material plasma. So it's something that, so there are strict limitations depending on the quality of the cut you want. So yeah, we'd have to take specific examples, which I'm also not the best person to ask you. So I would say, as a simple explanation, just the time that will take to cut through the freeze, but there are other limitations.
But do you see with innovation in the future we could overcome this?
Yeah, well,
How is
I
there-
think so. I think so.
Like these fiber lasers that I presented. I mean, when I studied, the list of manufacturing was either CO2 or neodymium YAG. Now, fiber lasers are a lot more recent. But still, you know, it's happening. It's not. If I didn't have to do this presentation, I wouldn't have known about it. But that's because there's a lot of people working in this space, and there's new lasers being.
It's, for example, something that we can observe in OCT, because when the technique was introduced, it generated the need of better light sources, because with longer wavelength we can go deeper. But then we have to remember that in eye we have different structures, so we have to avoid some particular light wavelengths to not be absorbed before they reach retina and so on. Then in the eye there's the need to do very fast imaging to avoid movement of eye. So in the beginning probably the measurement could take a few seconds, but it's not short enough measurement for ophthalmologists. What really inspired different research group to work on new light sources. So if there is a need and there is possibility to do something, people just try to do.
And often the need doesn't come from the same field. So the whole telecommunication, the whole of optical coherence tomography and imaging through endoscopes comes from the great development in telecommunication to understand fiber and propagation of light in fibers. And then it certainly turns out that it's very cheap to use fibers, so that in biomedicine they've been used a lot too, right? So.
Somewhat naively, we're told never to look at laser lights with the eye,
Yeah.
and if the laser is used for eye surgery, is it just a difference in power or duration? Or?
Yeah, it's also the difference in power and duration and where we go with our laser.
So that's what you're saying?
Yes, yes.
There are permissible exposure limits that are very strict, and so people using laser need to be aware of.
So we really need to be also very careful about different kind of power monitors, because actually one of our doctor working in LAI, he had an accident. He had patient, about 10 years old boy, who bought green laser power pointer on internet that cost about, I don't know, $30, and he just burned the part of his retina playing with. So.
But generally speaking, there's a classification from class 1 to 4, and then it's related to safety, to exposure, eyes, and other parts. And so class 3 and 4 are the most dangerous ones, so they should be operated only by knowledgeable personnel. What changes, for example, is the fact that even a lower power laser that it's in the infrared compared to a higher power laser that it's in visible range, which will trigger, though, if it's pointed to your eye, a blink reflex, whilst the infrared one may not. So the lower power one in the infrared could be a class 3 or 4, whilst the visible one may be a lower class just because you will react to it. So that's
Thank you. What can you say about the therapeutic properties of light? So if you think about sound, you can sit down and listen to music and you find that quite therapeutic. Is there a lot of research that's going on in terms of how people react and conditions that they have in response to different colours, and as opposed to burning something off actually non-destructive and
I'm going to take first. So I'm taking that you're not asking about.
It's not just that as well. We have a whole circadianism that asks the animal has a biological clock to it, and that is regulated by other things.
Yeah.
So there is definitely influence of light in those in that aspect of our whole body regulation. And it comes down to, as I said, the seasonal disorder as well. Places with low sunlight, with long winters, people get into depressed modes, and they use light as a therapy for that with the right wavelength as well. And when this comes into, you have to find the right wavelength where it actually has an effect. And I think there's not that much yet as well, but hopefully people will get more.
So I also read some article, I can't really hear details about research done in UK when they used green light mask for patients with neovascularization in the retina, because sometimes it happens that because of some disease there is increase in the number of vasculature, which is of course not good for us, because this vasculature will take nutrients that normally would take only normal blood vessels. And the purpose of this mask is to wear it during the night time when the metabolism of the retina is the highest, and just to slow down this metabolism and decrease the development of new vasculature. But as I said, I really didn't have much opportunity to read, but if it's true, it would be just a great thing to support ophthalmology.
I've often heard various postulated possible uses of light that you haven't mentioned. That's the use of light sails as a means of propulsion of spacecraft. I find this rather difficult to swallow, actually, because light, I can't see how light can actually produce a pressure. So simply put, if when light strikes a mirror, it's reflected back. So it comes to a stop and is emitted at the same velocity, same frequency, with no loss of energy. Therefore, how can it transmit any energy to the mirror? And
Well, I'm not aware of this particular application. I know it's not in space necessarily, in tissue, for example. Absorption of light generates pressure wave because that's another way of releasing power, right?
by heating the molecules.
Yeah. Well,
I think what you're talking is they're called light sails.
That's right, yeah.
Planetary Society has
Yeah.
And that's the fact that all the experiments that we carried out have found solar wind particles or electrons that given off by the filaments used to create the light, and they're the ones that actually make the pressure, not the light itself.
okay, yeah.
I mean, photons
I'd have
have
to
no
research
mass,
more.
therefore
But they do have momentum, and they do.
Yeah,
provide
that's
radiation
right.
pressure.
Yeah, the light can carry momentum.
Optical tweezers.
Yeah, optical tweezers,
They're just-
yeah.
yes.
That's right. There's a whole idea of being able to position single molecule of interest by using light, because light can carry momentum. And now I'm sure there's YouTube videos of trying to actually move a bigger and bigger particle, because normally they just move where they manage to shift on the micro-sized particles. But yeah, no, there is light can carry momentum, and so it can actually move particles. The details of this light cells, I'll have to read into it.
I've got macular degeneration, and each time I go to have injections, they take like a camera which whizzes across and does a little. I presume that's done with a laser, and it comes back with like a cross section of the
Yes,
back
so
of the retina.
this is OCT instrument, optical coherence tomograph, that allows to see different layers of retina,
Yeah.
and in this way see the progression of disease. So yes.
Is that a laser or is that just a?
Yes, it's a laser.
So obviously very weak. That's all.
Yes.
Yeah. It's an infrared laser.
Yeah, I've been imaged using OCT probably for the last 10 years. Hopefully I can still see.
Can I ask, can prolonged exposure to the lower grades of laser affect, like you're saying is like levels 1, 2, 3, 4, if you have a lot of levels 1 and 2, can they eventually cause a problem in sight?
I'm not in the regulatory business, so I don't personally. I don't think so. But I
Because
don't
like,
think so.
for example, going to a lot of laser light shows compared to going maybe to 1 or 2, that sort of thing.
No, I'd say you're safe, but don't stand exactly in front of the viewing system.
You know, the live show, you're not actually looking at the lasers, you're looking at the light is not part of it.
Yeah.
Absolutely.
Sometimes you do though get at
There's
least
so
a
many.
scattered wave back
Because
in
there's so many, they're gonna be
but it's so
direct.
fast that
Yeah.
it shouldn't, and it's visible, so it should.
Great. I just wanted to take the opportunity to thank you both for a brilliant presentation this evening. It's just been, you've covered so many different aspects of life, which is just what I had in mind. And I advised you, and you've surpassed anything that I expected. So I want to thank you for that. One of the applications of light which I found amazing is that I think it's the Lawrence Livermore National Facility outside of San Francisco.
National Edition facility,
Where they take just a simple beam of laser light, I think, and they're able to magnify it millions and millions of times, and then they concentrate it back onto a frozen hydrogen molecule to turn it into helium, and it seems to be one of the possible great renewable energy sources of the future. Do you know much about that?
Well, again, not my greatest area of expertise, but I think it's based on the concept of a phased array. So just you sounded like you knew something.
National Edition facility where they're trying to create fusion from that process, because that's what the sun is essentially doing. But it lasts for like probably a femtosecond or so, because they've been doing this for a number of years now. So they are actually creating fusion vapors, just evaporating.
Early days.
Yes.
Early days.
But the way I think they managed to get this laser being so powerful is by using, because there hasn't been a laser being so powerful to be on its own to be able to do this. So they're using interference again, but instead of using it within the same cavity medium, which is what generates the laser light for a single laser, they're trying to lock the phase of the waves, which can act constructively again from multiple laser sources, and that is a very difficult task to achieve. But if you do, then you can create a massive energy peak that will deliver enough energy to then refuse.
There's some brilliant YouTube clips just highlighting the principles involved.
Yeah.
It's really quite amazing.
Yeah.
They can do.
I love YouTube.